Number 49, solve the problem, and we're told a certain radioactive isotope has a half-life of approximately 1,350 years. How many years to the nearest year would be required for a given amount of this isotope to decay to 80% of that amount? And what we're going to do in the case of number 45 is we're actually going to use the equation here for exponential decay in this case to first find out what the rate of decay is for this isotope per year. So we're going to be solving for K first because we're going to have to use this equation twice. So the first time we use it, we are going to solve for K, and then once we have the K value, that constant, that rate of decay, we can then find out how many years it will take for the isotope to decay to 80% of the initial amount. So let's go through this step by step. So with the exponential decay function here, y sub 0, as we can see, is the amount or number present at time equals 0, t equals 0. So to make the math easy for ourselves, let's pretend that we're starting with 1 milligram of whatever this radioactive isotope is. So we'll say that y sub 0 is 1. Y is how much is present after the decay process has taken place. Well, if we're talking about the half-life of this isotope and we're starting with 1, well, how much is left after half has decayed? Well, that would just be 0.5, wouldn't it? We start at 1, half decays, so we're left with 0.5. Now we know E is Euler's number, so nothing to solve for there. The K is what we're actually looking for, that constant, the rate of decay for this isotope, and T is the time that it takes, the half-life of this isotope. How long does it take for half this isotope to decay? Well, that's 1,350 years. So using all of this information, we'll plug it into this exponential decay function, solve for K, and then we can go about finding how many years it'll take for 80% of this isotope to be remained. All right, so 0.5, that's our y, equals y sub 0, which we're saying is 1, times e to the k, well again, we're trying to find k, so we don't know what that is, times t, and the half-life is 1,350 years. All right, fair enough. Let's go ahead and clean this up just a little bit. And so we're going to say 0.5 equals, and we're going to get rid of this 1 here, right? 1 times this quantity is still e to the k 1350. So we can get rid of that 1. So we'll say e. And we're used to seeing the numerical coefficient out front, so we'll rewrite this as 1350k. All right, since we are working with E, Euler's number, let's go ahead and take the ln of both sides, the natural log of both sides. And that will give us ln e to the 1350k here on the right. And because we've taken the natural log here on the right, that tells us that we can pull this exponent down out front, can't we? So we end up with ln of 0.5 equals 1350k times ln of e. As we've looked at in several of the previous videos, we know ln e is simply 1, so we can go ahead and get rid of it. And now we're left with ln 0.5 equals 1350k. We want k all by itself. We want to know what the actual rate of decay for this isotope is. So let's divide by 1350 on both sides. Here on the right it cancels out, and so we're left with just k. So k is approximately, and I went ahead and worked this out beforehand, ln 0.5 divided by 1350k is negative 0.000, and I'm going to go ahead and round my answer 513. So this is the rate of decay for this particular radioactive isotope. And now that we've solved for k, 0, now that we've solved for k, we can go ahead, take this k value, plug it back in to our equation with some other information and find out just how many years it will take for this isotope to decay to 80%. All right, so again, let's pretend that we're starting with a single milligram of this isotope. How much are we looking for this isotope to decay to? Well, we're looking for it to decay to 80%. So how can we write 80% of 1 milligram? Well, that would just be 0.8 times 1, right? Or, in this case, just 0.8. So our Y value is 0.8. Again, E we already know, Euler's number, nothing to solve for there. We just solved for K, didn't we? So this K value is negative 0.000513, and this time we're solving for T. We want to know how long it's going to take for 80% of our single milligram of this isotope to be remaining after the decay has taken place. So now that we have all this information, let's plug it in. So we have 0.8 equals 1 times e to the negative 0.000513 times t. We're solving for t now. Again, let's go ahead and clean this up a little bit, and for the sake of time, I'll just erase that 1 there. So we have 0.8 equals e to the negative 0.000513 t. We want to take the ln of both sides, so we have ln of 0.8 equals the ln of e to the negative 0.000513 t. Because we took the ln here on the right, we can go ahead, take this exponent, move it down out front, which gives us ln of 0.8 equals negative 0.000513 t ln e. We know ln e is just 1, so that goes away. We want t all by itself. We're solving for time, so we'll divide on both sides. And we're going to have t is approximately, and are we rounding here? To the nearest year. Yes, we are. So let's go ahead, bring up our calculator, and see what we end up with. So the ln of 0.8 divided by negative 0.000513 gives us 434.97. Again, we're rounding to the nearest year, so we'll go ahead and round this to 435 years. All right, so again, we had to use this equation for exponential decay twice. The first time we used this equation, we were solving for K, the constant, the rate of decay for this isotope, because notice we needed this rate of decay in order to solve for T, the time it takes for 80% of this isotope to remain. All right, so we solved for K first using the half-life information, and then once we had K, we were able to use that K value to solve for T. All right, in this case, number 49, 435 years is how long it will take for this isotope to decay to 80%.